Our universe hides its most massive secrets in plain darkness. Supermassive black holes, those legendary giants, are not all where we expect them to be. This video will show you how modern astronomy is hunting for the invisible ones, the rogue supermassive black holes drifting silently through the void between galaxies. By the end, you will understand how finding them could rewrite the cosmic rulebook. We are searching for phantoms that could outnumber the black holes we see, gravitational ghosts born from ancient galactic collisions. What does it mean for our map of reality if the universe's heaviest anchors are not anchored at all? How do you find something that emits no light and hides in endless night? The answers are waiting in the data of our most powerful telescopes. What would you expect to find in the deepest dark between the stars? The cosmic rulebook we have written is beautifully simple. For decades, our fundamental model has stated that every large galaxy is built around a supermassive black hole. This is not a coincidence, but the very foundation of galactic architecture. Imagine a city with a single, immense central power station. Everything revolves around it, from the traffic flow of stars to the shape of the streets, the spiral arms. That is the role a supermassive black hole plays. It forms over billions of years through a relentless process of feeding, a process astronomers call accretion. Gas, dust, and even entire stars are pulled in by its immense gravity, swirling into a superheated disk of material before vanishing across the event horizon. This violent feast is not quiet. It releases staggering amounts of energy, often outshining every star in the galaxy combined. When this happens, we call it an active galactic nucleus, or a quasar if it is exceptionally bright and distant. These are the brilliant beacons we have used for so long to map the locations of supermassive black holes across the universe. They are the standard signature, the predictable heartbeat at the center of a cosmic body. This model is elegant and has served us well, explaining the furious energies we see and the majestic rotations of galaxies. It paints a universe of order where the most massive objects are also the most anchored, the fixed points around which everything else dances. But what if our map is incomplete? What if, by only looking for the light, we have been missing the silent giants who have left the dance floor entirely? Our elegant model of the universe began to crack under the weight of its own predictions. Astronomers running sophisticated computer simulations of galactic collisions noticed something strange, a violent detail that the old rulebook could not explain. When two galaxies merge, it is a slow, cosmic dance spanning hundreds of millions of years. Their spiral arms tangle, stars are flung into new orbits, and crucially, their two central supermassive black holes begin to spiral toward each other. For a long time, we assumed they would eventually meet and merge into one even larger black hole. But the simulations revealed a different, more dramatic possibility. As the two black holes whirl around one another in their final moments, they can emit powerful, lopsided ripples in spacetime itself, what we call gravitational waves. If these waves are emitted more strongly in one direction, the conservation of momentum demands a reaction. Think of firing a rocket engine in space. The craft shoots forward while the exhaust blasts backward. In this cosmic version, the unbalanced gravitational waves act like that exhaust, delivering a tremendous kick to the newly merged black hole. The result is not a peaceful union at the new galactic center. Instead, the newborn supermassive black hole can be ejected, recoiling from the scene of the collision at speeds of thousands of kilometers per second. In an instant, the galaxy's central anchor is ripped away, becoming a rogue, a wanderer cast into the intergalactic darkness. This was not just a theoretical glitch, it was a logical and violent outcome written into the laws of physics. The question shifted from if this could happen to where are all the orphans it must have created. This creates the ultimate cosmic hide and seek. A rogue supermassive black hole, stripped from its galactic home, carries a profound silence with it. In the bustling center of a galaxy, it was constantly fed. Rivers of gas and swarms of stars provided a steady stream of material, which swirled into that brilliant, superheated accretion disk, a lighthouse beacon announcing its presence across the universe. But out in the deep, intergalactic void, the pantry is nearly empty. There is almost no gas, no dense clusters of stars to consume. Without this fuel, the black hole cannot create an accretion disk. It emits no X-rays, no brilliant flares of radiation, no telltale glow. It becomes a true dark object, its presence defined solely by its immense gravity, a ghost that bends light but creates none of its own. Compounding this challenge is the sheer, mind-numbing scale of the emptiness it inhabits. The average distance between galaxies is millions of light years. If one of these wanderers is drifting through that profound darkness, it is incredibly far from any source of light we could use to indirectly spot it. Our most powerful telescopes work by collecting photons, particles of light. We cannot take a picture of an object that does not send any our way. Direct imaging is for now a fantasy. So we are left searching for a shadow in a shadow, a silent titan adrift in an ocean of night, using only the subtlest of clues written in the fabric of space itself. The only hope for spotting these silent giants lies in a quirk of gravity itself, a phenomenon known as gravitational lensing. According to Einstein's theory, a massive object warps the space around it, like a heavy ball placed on a stretched rubber sheet. Any light traveling through that warped space will follow a curved path. When the alignment is just right, a foreground object can act as a cosmic magnifying glass, bending and focusing the light from a more distant star or galaxy behind it. For a supermassive black hole adrift in the void, this effect offers a fleeting, almost ghostly signature. It is called microlensing. Here is how it works in the darkness between galaxies. Imagine a single, distant star shining billions of light years away. Its light travels across the universe in a straight line toward us. Now, picture a rogue supermassive black hole drifting silently across that precise line of sight. As it passes in front of the distant star, its immense gravity bends the star's light rays around it, acting as a temporary lens. From our perspective, the background star does not move, but it appears to briefly brighten, then fade, as the black hole's gravitational focus sweeps over it. This brightening can last for months or even years, a slow-motion flash in the cosmic dark. The challenge is that this signal is extraordinarily subtle and rare. It requires a perfect chance alignment of three objects, us, the wandering black hole, and a distant background star, across unimaginable distances. The brightening is also temporary and never repeats. We have to be looking at exactly the right patch of sky at exactly the right time with instruments sensitive enough to catch that slow, mysterious flicker. It is like trying to spot a single firefly lighting up for a moment somewhere in a forest the size of a continent, while only being allowed to glance once. Yet this faint hope is what drives the hunt, a search for the most elusive shadows cast by the universe's heaviest phantoms. This search for a single flicker is perhaps the greatest data challenge in modern astronomy. To understand why, you must first grasp the sheer scale of the emptiness involved. The space between galaxies is not just big, it is overwhelmingly, almost incomprehensibly vast. If our Milky Way galaxy were the size of a dinner plate, the distance to our nearest galactic neighbor, Andromeda, would be about 7 meters away. But the rogue black holes we are hunting are not necessarily on a neat line between us and another galaxy. They are adrift in the millions of cubic light years of profound nothingness in between. Now, within that unimaginable volume, we need a specific 1 in a billion alignment, a distant background star, a wandering black hole, and our line of sight from Earth all have to line up with perfect precision for the microlensing event to even be detectable. The probability of catching such an alignment for any given star is astronomically low. It is less like finding a needle in a haystack and more like searching for a single, specific grain of sand on every beach on Earth, while knowing that grain only glows for a few minutes every century. This is why, for decades, the idea of finding one seemed nearly hopeless. We simply did not have the tools to monitor enough of the sky with enough precision over long enough periods. But that is changing, driven by a new era of astronomical surveys that do not just look at the sky, they watch it continuously and with incredible detail. Missions like the European Space Agency's Gaia satellite are building an unprecedented three-dimensional map of our galaxy by measuring the positions and motions of over 1 billion stars with exquisite accuracy. By tracking these stars over years, it can detect the tiny, telltale brightening caused by a foreground object's gravity. But the real game changer is on the horizon. The Vera Rubin Observatory, set to begin operations in Chile soon, will take this watch to a whole new level. With its enormous mirror and giant camera, it will scan the entire visible southern sky every few nights for a decade, creating a time-lapse movie of the universe. It will not just see static pictures, it will see change. It will catalog tens of billions of stars and galaxies, generating a flood of data so immense that finding a single, slow brightening event from a rogue black hole will require sifting through petabytes of information with advanced algorithms designed to spot the most subtle anomalies. The hunt has shifted from a question of pure chance to one of data mining, of finding a single, extraordinary story hidden within quintillions of lines of cosmic code. The data flood from these new observatories has already begun to yield strange and compelling whispers from the dark. One of the most tantalizing hints came not from the future, but from a careful re-examination of the past, a single line of light recorded over a decade ago. In 2011, two independent sky survey projects, one called OGLE and another named MOA, both recorded the same mysterious flicker from a star in our own galactic bulge. The event was catalogued under a joint, cumbersome name, MOA-2011-BLG-191/OGLE-2011-BLG-0462. For years, it was just another entry in a vast database of microlensing events, most of which are caused by faint stars or brown dwarfs. But when astronomers finally had the computing power and sophisticated models to analyze its unique light curve in detail, the story changed. The pattern of brightening and the duration of the event, which lasted about 270 days, pointed to an invisible lens of extraordinary density. The calculations were startling. The object causing the distortion had a mass roughly 7 times that of our Sun, yet it emitted no light of its own. The only compact object that fits such a profile is a black hole. This was monumental. It was not the supermassive wanderer we are ultimately hunting, but something equally profound. A stellar mass black hole drifting alone through the interstellar space within our own galaxy, completely isolated from any companion star. For the first time, we had strong evidence of a black hole detected not by the X-rays from a feeding disk, but purely by the silent fingerprint of its gravity bending the light of a distant sun. This candidate, while smaller, proved the principle beyond theory. It demonstrated that our techniques could find the invisible, that these ghosts do exist in the isolation we predicted. More importantly, it validated the entire methodology of the hunt. If we can find one lonely black hole of 7 solar masses using data from over a decade ago, what might we find when we apply the same ruthless analysis to the torrent of data from the next generation of sky watchers, searching in the far vaster emptiness between the galaxies themselves? That single flicker from the galactic bulge was a powerful clue, but science demands confirmation. In 2022, the Hubble Space Telescope delivered it. For 6 long years, Hubble's sharp eye patiently tracked the same patch of sky, measuring not just the brightness of stars, but their precise positions with a level of accuracy akin to spotting a coin's edge from 3,000 kilometers away. The target was that same mysterious lensing event from 2011. Hubble was not looking for another flash of light. It was hunting for a different signature entirely, a tiny, persistent wobble. This technique is called astrometric microlensing. Here is the brilliant logic behind it. When the invisible black hole passed in front of the distant star, it did more than just magnify its light. It also shifted the star's apparent position in the sky by a minuscule amount as its gravity deflected the starlight's path. Imagine looking at a streetlight through the rippling air above a hot grill. The light seems to shimmer and dance. The black hole's gravity creates a similar, though perfectly predictable, distortion. By measuring this incredibly subtle positional shift over years, Hubble's team could perform a cosmic autopsy. They could calculate the lensing object's mass, its distance, and most importantly, its velocity through space. The numbers were definitive. The object was roughly 7 times the mass of our Sun, drifting alone about 5,000 light-years away, moving at a brisk 45 kilometers per second. This velocity was the final piece of evidence. It was too fast to be a slow-moving, faint star, and it matched the expected kick a black hole would receive from the supernova explosion that birthed it. This was not just another candidate. It was the first unambiguous detection of an isolated stellar mass black hole in our galaxy, confirmed purely by the silent warping of spacetime. The significance of this quiet discovery cannot be overstated. It proved that our methods work. We can, with patience and extreme precision, find the invisible population of black holes that emit no light. We have the tools to see their gravity. This confirmation is the crucial bridge in our hunt. It validates the entire search strategy on a smaller, more local scale. If we can find a single, city-sized black hole drifting through our galactic neighborhood using these principles, then the foundational concept is sound. The leap to finding a continent-sized, supermassive wanderer in the intergalactic void is no longer a fantasy. It is the next logical step in a proven scientific process. The dark population is real, and we have just learned how to take its census. The confirmation of that lone stellar black hole was a blueprint for a far grander hunt. We have proven the method on a local scale, but the ultimate prize remains hidden in the deeper dark, the supermassive wanderers. Finding one would be a different kind of challenge entirely, not just a bigger version of the same signal. The difference lies in the sheer scale of their influence. A stellar black hole might lens a single star for a few hundred days. A supermassive black hole with millions or billions of times the mass warps spacetime on a colossal scale. Its gravitational reach is so vast that it would not just magnify a single distant star, it could distort the light of an entire galaxy behind it. The lensing event would not be a brief flicker, but a slow, majestic distortion lasting for years, perhaps even decades. We would be looking for a subtle, persistent stretching of a background galaxy's image into a faint arc or even a complete ring of light, a phenomenon called an Einstein ring. This signature would be unmistakable, a ghostly halo in the void created by an invisible titan's gravity. Yet, despite knowing what to look for, no definitive detection has been made. The challenge is one of probability and patience. The perfect alignment for such an event is even rarer. We need a rogue supermassive black hole, a distant background galaxy, and our line of sight to all line up across hundreds of millions of light-years. Our telescopes must also monitor the same patch of the deep, extragalactic sky with extreme precision for a very long time, searching for those slow, graceful distortions to emerge from the darkness. It is a waiting game on a cosmic clock, but with new observatories now scanning the entire sky repeatedly, that wait may finally be over. The first ghostly ring could appear in the data at any moment. The numbers suggested by these simulations are not just surprising, they are staggering. While we have confirmed only one isolated stellar black hole in our own galaxy, the theoretical population of their supermassive cousins could be immense. Cosmological models that recreate the violent merger history of our universe paint a picture of a cosmos littered with these gravitational castaways. In a single, massive cluster of galaxies, a place where galactic collisions are frequent and violent, simulations suggest there could be thousands of wandering supermassive black holes adrift in the intracluster space. They are not at the hearts of galaxies, but floating in the hot, thin gas between them, invisible anchors with no galaxy to hold. Zoom out further to the scale of the entire cosmic web, and the estimate grows exponentially. Some theoretical studies propose that the number of rogue supermassive black holes could rival, or even exceed, the number that are safely anchored in galactic centers. This is a complete inversion of our old understanding. We once thought every giant needed a throne. Now, the models whisper that for every supermassive black hole sitting in a galactic core, there might be another one or more, exiled to the darkness, drifting like silent monarchs who have lost their kingdoms. This raises a profound and unsettling question. If these phantoms are so common, why have we not seen them yet? The answer circles back to the profound emptiness they inhabit. 1,000 wanderers in a galaxy cluster sounds like a lot until you grasp the sheer volume of that cluster. It is like searching for 1,000 individual marbles scattered across an area the size of the entire Pacific Ocean. The density remains incredibly low, making any single alignment with our line of sight a rare cosmic event. Yet, the statistical weight of these predictions is compelling. They tell us that our previous census of the universe's most massive objects was likely a significant undercount. We have been counting the kings in their castles, while entirely missing the ones wandering the vast, dark countryside between. This hidden population is not a fringe curiosity. It could be a fundamental feature of how the universe evolved. A silent testament to the brutal, merging history that built the galaxies we see today. But galactic mergers are not the only factory that could produce these dark wanderers. To truly grasp their potential numbers, we must look further back to the very dawn of time. In the primordial universe, before the first stars and galaxies had fully assembled, conditions were unimaginably different. Vast clouds of pristine hydrogen and helium gas, uncontaminated by heavier elements, could have collapsed under their own gravity in a uniquely direct way. Under this specific, intense pressure, a supermassive black hole could form in a single, catastrophic step, bypassing the need for a star to die first or for smaller black holes to merge. This is the direct collapse model, a cosmic shortcut to creating a giant. Think of it like building a skyscraper. The standard method is to assemble it floor by floor, brick by brick, over years. That is like a black hole growing through accretion and mergers. The direct collapse method would be if the entire structure materialized almost instantly from a single, colossal pour of concrete. These primordial black holes born in the cosmic infancy would have no galaxy to call home from the very beginning. They are not exiles, they are nomads by birthright, wandering the expanding universe since its earliest chapters. Their formation did not require violence between galaxies, only the unique physics of a younger, denser cosmos. This pathway suggests a population of wanderers that is ancient, perhaps even more numerous than those created by later mergers, drifting through the void for nearly the entire history of everything. There is another, quieter process at work, one of cosmic theft on a grand scale. When small dwarf galaxies fall into the immense gravitational well of a massive galaxy cluster, they face a brutal environment. The space between galaxies in a cluster is not empty, It is filled with a thin, searingly hot gas. As a dwarf galaxy plows through this intergalactic medium, it experiences a relentless drag, a process called ram pressure stripping. This can tear away its gas, the very fuel for future star formation, but the theft can go deeper. The cluster's collective gravity, along with close encounters with other galaxies, can also pull stars right out of the dwarf galaxy's outskirts. This gradual dismemberment is known as tidal stripping. If the dwarf galaxy hosts a small, central supermassive black hole, that black hole can be stripped away along with the stars, left orphaned in the cluster's vast interior. Unlike the dramatic recoil from a major merger, this is a slower, more insidious form of abandonment. The black hole is not kicked out, it is left behind as its tiny home is slowly dismantled around it. This pathway creates wanderers in the bustling downtown of galaxy clusters, adding to the invisible population floating between the major galaxies. It shows that you do not need a colossal collision to create a rogue. Sometimes a slow and steady erosion is enough. Each of these pathways, from violent mergers to primordial birth to quiet stripping, contributes its own stream of dark wanderers to the cosmic sea. This multiplicity of origins is why the theoretical numbers are so compellingly high. We are not looking for a single type of phantom from one specific event. We are searching for an entire demographic of darkness, born from different chapters of cosmic history through different physical processes. Some are ancient relics from the universe's first moments, others are recent exiles from galactic wars, still more are casualties of a slower environmental dissolution. This diversity makes the hunt even more fascinating. If and when we finally detect one of these supermassive intergalactic wanderers, its properties, its speed, its location could act as a forensic clue telling us which cosmic factory produced it. Was it born in fire, in simplicity, or in slow decay? The answer would be a direct message from the past, etched not in light but in the silent geometry of warped space. The search for these dark wanderers touches on one of the greatest mysteries in all of science, the nature of dark matter. For decades, we have known that most of the matter in the universe is invisible, a substance that does not emit, absorb, or reflect light, yet exerts a powerful gravitational pull on everything we can see. We call it dark matter, and its true identity remains unknown. This leads to a compelling, though highly speculative, question. Could some portion of this elusive substance be made of black holes, particularly those ancient, primordial ones born in the early universe? If the direct collapse model created a vast population of wanderers in the cosmic dawn, and if they were numerous enough, their combined gravity could potentially explain some of the effects we attribute to dark matter. It is a tantalizing idea, a single solution to two profound puzzles. Instead of an exotic, undiscovered particle, the missing mass could be an astronomical object we already understand, just one we have not been able to see. This theory, however, is fiercely contested. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, place tight constraints on how much of the universe's mass could be tied up in compact objects like black holes. The delicate patterns in that ancient light suggest that while black holes could contribute, they are unlikely to be the dominant component of dark matter. The gravitational microlensing surveys that found our first isolated stellar black hole have also largely ruled out a universe teeming with planet-sized or star-sized primordial black holes as the primary dark matter candidate. But the door is not completely closed for the supermassive ones. Their immense size means they would be far fewer in number to account for the same gravitational effect, potentially slipping through the observational cracks of previous searches. Finding even one primordial supermassive wanderer would instantly elevate this from a fringe idea to a serious line of inquiry. It would prove such objects can form and survive, and it would force us to recalculate their possible numbers across cosmic history. The stakes of the hunt, therefore, extend far beyond cataloging exotic orphans. They reach into the fundamental architecture of reality itself, asking if the universe's darkest secrets are held by its darkest objects. This brings us to a profound and deeply theoretical frontier. A rogue supermassive black hole drifting in perfect isolation presents a scenario that pushes our understanding of physics to its absolute limit. In the bustling center of a galaxy, a black hole is partially clothed, its immense gravity shrouded by the brilliant, chaotic whirlpool of its accretion disk. This disk, glowing with fierce radiation, acts as a kind of visible boundary, a final, luminous testament to the physics at play before matter vanishes forever. But strip that away, remove all the gas, all the dust, every last shred of illuminating material. What you are left with is something far more stark, a gravitational singularity exposed to the universe with no veil. Astronomers sometimes call this a naked singularity. It is a point of infinite density, where the laws of physics as we know them simply break down, surrounded only by its event horizon, the point of no return. In a normal setting, that event horizon is hidden from our view by the very processes that feed it, but for our wanderer, there is no obscuring light show. Theoretically, the event horizon itself becomes the only surface, a perfect black sphere against a perfect black sky. This is not just a black hole, it is the purest expression of one, a near-perfect laboratory for testing Einstein's theory of general relativity in its most extreme and unadorned form. All the bizarre predictions, the severe warping of time and space, the one-way nature of the horizon, they all exist in their most pristine state, uncomplicated by the messy astrophysics of infalling matter. The problem is, a perfect black sphere against a perfect black background is, by definition, invisible. Its purity is its ultimate camouflage, so how could we ever observe the behavior of a naked singularity? The answer lies not in seeing it, but in seeing its severe distortion of everything around it. If we were ever fortunate enough to witness a lensing event caused by such an object, the pattern of distorted light would be the cleanest possible signal. With no accretion disk to create flickering or extra glow, the lensing signature would be a pure product of gravity's geometry, uncontaminated. Analyzing that distortion with extreme precision could allow us to probe the nature of the event horizon itself in ways that are impossible with an active, feeding black hole. We could test if the predictions of general relativity hold perfectly at this ultimate boundary. We could search for tiny deviations that might hint at new physics, a crack in the elegant theory that has guided our understanding for a century. Finding a rogue supermassive black hole would not just be about discovering a new class of object. It would be about finding the universe's most perfect gravitational laboratory, a silent, dark instrument floating in the void, waiting to teach us about the fundamental fabric of reality. But pure gravitational lensing is not our only potential window into this darkness. There exists another, far more violent and fleeting signal that could betray a wanderer's presence, a cosmic scream in the night. This method revolves around a phenomenon known as a tidal disruption event. The principle is brutally simple. A star going about its normal life has the profound misfortune of passing too close to a black hole. The side of the star facing the black hole feels a much stronger gravitational pull than the side facing away. This difference in force, the tidal force, stretches the star horizontally while compressing it vertically. The star is not simply swallowed whole, it is shredded, pulled apart into a long, thin stream of superheated gas. This stream then swirls around the black hole, colliding with itself in a chaotic frenzy, and in the process, it releases an intense, short-lived flare of radiation across the electromagnetic spectrum, from X-rays to visible light. For a few months, this dying star's material can outshine an entire galaxy. In a normal galactic center, we see these events occasionally, and they confirm the presence of the resident supermassive black hole. But the same physics applies in the deep void. If a rogue supermassive black hole on its endless journey were to drift through a sparse star cluster or the outskirts of a nebula, it could, by sheer chance, come close enough to a star to tear it apart. The resulting flare would be a brilliant, unmistakable beacon, a temporary lighthouse flashing in the intergalactic darkness, signaling the location of an otherwise invisible giant. The challenge, once again, is probability. The spaces between galaxies are so overwhelmingly empty that the chance of a black hole encountering a star there is vanishingly small. It is like hoping to see a single flash of lightning strike a specific, lone tree in a million square miles of desert. Yet, because these flares are so incredibly bright, if one did occur, our telescopes would almost certainly see it. Surveys that scan large swaths of the sky for transient events, for things that change and flare, are our best hope for catching this signal. The flash would be brief, perhaps lasting only a season in cosmic terms, but its location would be the true clue. It would appear not in the heart of a galaxy, but in the profound nothingness between them, a brilliant anomaly with no galactic core to explain it. Finding such an event would be like discovering a single, raging fire in the middle of the open ocean with no ship in sight. It would point unequivocally to a hidden cause, a dark passerby that left a devastating, luminous calling card. While gravitational lensing is the method of patience, the silent fingerprint, a tidal disruption flare would be the method of sudden drama, a catastrophic and revealing accident. Both are long shots, but in a universe this vast and ancient, even the rarest events are bound to happen somewhere, sometime. Our task is to watch and to be ready for the flash. The search for these phantoms hinges on a subtle but critical choice in our observational strategy. We are not just looking, we are measuring, and the type of measurement we prioritize could determine what we find. The dominant technique for decades has been photometry, the precise tracking of an object's brightness over time. This is the method that first spotted the flicker of our lone stellar black hole. It is powerful, relatively straightforward, and perfect for detecting the classic signature of a microlensing event, that smooth rise and fall in a star's light. For most searchers, especially those scanning millions of stars at once, photometry is the workhorse. It tells us something is there, bending light, and from the shape and duration of the brightening curve, we can estimate the lensing object's mass and distance. Yet, for the grandest quarry, the supermassive wanderers, photometry has a fundamental limitation. It provides only part of the story. The light curve alone cannot tell us the true motion of the lensing object across the sky. This missing piece, the velocity, is the key to unlocking everything else. Without it, our understanding of the object remains frustratingly incomplete. We know its gravitational strength, but not its direction or speed through the cosmic void. This is where the second, more demanding technique enters, astrometry. This is the science of measuring the precise positions of celestial objects with almost unimaginable accuracy. Instead of just watching a star brighten and fade, astrometry watches it dance. As the invisible black hole's gravity bends the starlight, it also minutely shifts the star's apparent position in the sky. The star appears to trace a tiny, elliptical loop over the months or years of the lensing event. This astrometric wobble is the game changer. By meticulously mapping this loop, astronomers can solve for all the parameters of the system. They can calculate not just the lens's mass, but its exact transverse velocity, its proper motion across our line of sight. This transforms a detection from a simple yes or no into a full forensic profile. For a slow-moving, supermassive object, this distinction is everything. Its lensing event would be extraordinarily long, perhaps lasting decades. A photometric survey might see a very slow, gradual brightening that could be mistaken for other, more mundane astrophysical processes, or simply lost in the noise of long-term data. But the astrometric signature, that persistent, graceful shift in position, would be unique and unambiguous. It is a cleaner signal for a slower, more massive object. Hubble's confirmation of the stellar black hole proved the supreme power of this method. It took 6 years of painstaking positional measurements to extract that tiny wobble, but the result was a complete portrait, a velocity and a mass, turning a candidate into a confirmed discovery. For the supermassive wanderers moving with the stately pace of giants through the intergalactic deep, astrometry may be our only true path to certainty. It is the difference between seeing a shadow move and being able to chart its exact path through the dark. The astrometric precision required for this hunt has found its perfect instrument in the silent vigil of the Gaia spacecraft. Unlike telescopes that stare into the distant universe, Gaia's mission is one of profound, patient measurement. It does not simply look at our galaxy, it weighs it, maps it, and tracks its every subtle motion. From its vantage point at a stable gravitational point beyond Earth's orbit, Gaia has spent years performing the largest and most precise celestial census ever attempted. Its goal is to measure the positions, distances, and movements of over 1 billion stars in the Milky Way with an accuracy that borders on the unbelievable. To grasp this precision, consider that Gaia could pinpoint the diameter of a human hair from 1,000 kilometers away. It is this godlike resolution that transforms the search for invisible masses from a hopeful gamble into a systematic investigation. Every star in its catalogue is not just a point of light, but a data point in a vast, three-dimensional and, crucially, a moving model of our galactic neighborhood. Gaia observes each of its billion target stars about 70 times over its operational lifetime, building up not a snapshot, but a time-lapse movie of stellar motion. This dynamic map is the key. When an invisible, massive object like a wandering black hole passes near the line of sight to one of these stars, its gravity will induce 2 distinct signatures. The first is the photometric brightening, the classic microlensing flash. But the second, and for Gaia often the primary signal, is that tiny astrometric wobble, the star's apparent position shifting by micro-arcseconds as its light is deflected. Gaia's repeated, hyper-accurate measurements are designed to catch exactly that kind of subtle dance. It is constantly scanning the sky, not for new, brilliant phenomena, but for the quiet, persistent displacements of the familiar. Each star's path across the heavens is meticulously charted, and any deviation from its expected straight-line motion becomes a potential clue. A single, unexplained wiggle in the trajectory of a distant sun could be the fingerprint of a dark passerby. While Gaia's primary focus is the stars of our own Milky Way, its methodology is a proof of concept for the universe. It demonstrates that we have the technological capability to measure space itself with enough fidelity to sense the whispers of unseen gravity. The data Gaia is compiling is a treasure trove for forensic astronomers, who are now developing sophisticated algorithms to sift through the motions of 1 billion stars, searching for the rare, telltale patterns that signal a massive, invisible companion. It is a digital hunt for ghosts in the machine, where the machine is the most precise map of the galaxy ever created. Every anomalous curve in a star's journey is a question, and one of those questions may soon point directly to a dark wanderer hiding in the galactic shadows, its presence betrayed only by the slightest tremble it imparts on the fabric of our map. The pristine signal we dream of is often obscured by cosmic imposters. The universe is filled with dark, drifting objects that are not black holes, yet can produce an almost identical flicker in our telescopes. A rogue, Jupiter-sized planet flung from its solar system and wandering alone can lens a background star. So can a brown dwarf, a failed star too small to ignite nuclear fusion, glowing only with a faint, deep red heat. Even a very faint, ancient red dwarf star, almost invisible at interstellar distances, can mimic the gravitational signature we are searching for. all of these objects are dark to our optical telescopes, and all can cause a microlensing event with a similar brightening curve. This creates a fundamental challenge in our hunt. When we see that slow brightening in the data, the immediate question is not just what is it, but what else could it possibly be? The initial photometric signal, the change in brightness, is merely an invitation to investigate, not a confirmation. It tells us something massive and dark is there, but it cannot, on its own, reveal the true nature of the beast. A supermassive black hole and a lonely gas giant are separated by a factor of billions in mass, yet from a purely photometric lensing perspective, they can appear frustratingly similar if the alignments and distances are just right. The duration of the event provides a clue. Longer events typically point to more massive lenses, but it is not definitive proof. This ambiguity is why every candidate detection triggers a rigorous process of elimination, a cosmic detective story where the goal is to rule out every other possibility. The hunt does not end with the flicker, it begins with it. The real work starts in the aftermath of that first alert, as astronomers around the world turn a coordinated array of eyes toward the anomaly, searching for the one piece of evidence that separates a phantom giant from a mere dark dwarf. This next phase requires looking at the object in a completely different way, not for the light it bends, but for any faint glow it might emit on its own. The tool for this is multi-wavelength follow-up observation. While the object may be dark in visible light, it could still betray itself in other parts of the electromagnetic spectrum. A brown dwarf, for instance, will glow with a deep infrared signature, a warmth left over from its formation. A faint, cold star will emit specific radio waves. Even a rogue planet with a hot, volcanic core might leak a tiny amount of infrared heat. A team receiving a microlensing alert will immediately task infrared telescopes like NASA Spitzer or radio observatories to stare at the exact coordinates. If they detect any emission, any thermal glow or radio whisper, the mystery is likely solved. They have found a dark star or a failed star, not a black hole. The true supermassive wanderer, in its perfect isolation, would offer nothing. It would be silent across every wavelength, from radio waves to gamma rays. Its confirmation therefore relies on a profound absence, a null result that becomes the strongest evidence. We must prove it is not just dark, but perfectly, completely black. Only after every other source of emission has been ruled out can the extraordinary claim of a rogue black hole begin to stand. This meticulous cross-examination transforms a curious signal into a scientific fact, ensuring that when we finally announce the discovery of a ghost, we are not simply being fooled by a shadow. This search for silent giants is intimately connected to another new window on the universe, one that listens for the faintest ripples in reality itself. Gravitational-wave astronomy has transformed our ability to hear the cosmos, detecting the violent mergers of black holes and neutron stars through the subtle stretching of spacetime. For the story of rogue supermassive black holes, this field provides both the origin story and a future detection method. The process begins long before a black hole is cast into exile with a slow and stately cosmic dance. When two galaxies merge, their central supermassive black holes eventually sink to the new core, forming a binary pair. These two titans, each millions of times the mass of our Sun, begin to orbit one another. As they spiral closer over millions of years, they churn the fabric of spacetime, emitting a steady, low-frequency rumble of gravitational waves. This is not the sharp chirp heard from stellar mass black holes, but a deep, persistent hum, a bass note in the symphony of the universe. Detecting this hum is the primary mission of a future space-based observatory called LISA, the Laser Interferometer Space Antenna. LISA will be a trio of satellites flying in a giant triangle, using lasers to measure minute distortions in the distance between them, distortions caused by passing gravitational waves. Its design is tuned specifically to hear the low-frequency song of these supermassive binary black holes as they circle each other in the hearts of distant, merging galaxies. The data from LISA will be a revolutionary census, allowing us to map the population of these impending mergers across cosmic history. But the story does not end with the detection of the hum. That hum grows louder and higher pitched as the two black holes spiral inward faster and faster until they finally collide and become one. It is in that final, violent moment that the universe can deliver its cosmic kick. If the merger is lopsided, emitting gravitational waves more powerfully in one direction, the newborn black hole recoils in the opposite direction, sometimes with enough velocity to escape its galaxy entirely. This creates a direct and profound link between two different kinds of observation. LISA would hear the final moments of the inspiral and the merger itself, the crescendo of the dance. Then, years or decades later, a telescope like the Vera Rubin Observatory or the James Webb might, through a patient microlensing survey, spot the resulting rogue black hole as it begins its lonely journey through the intergalactic void. One instrument hears the birth cry of the exile, the other eventually sees its shadow. Together, they would tell the complete story, from a paired dance in a galactic core to a solitary phantom in the dark, connecting the sound of creation to the silence of its aftermath. This synergy turns theoretical prediction into observable narrative, allowing us to trace the full life cycle of these dark giants from beginning to endless wandering. The void between galaxies is not all the same. To understand where we might find these phantoms, we must distinguish between two profoundly different kinds of darkness. First, there is the true intergalactic wilderness. This is the space between distinct galactic structures, a near-perfect vacuum spanning millions of light years. Here, a rogue supermassive black hole is in the ultimate isolation, a ship sailing an ocean with no other vessels in sight and no ports on the horizon. The density of matter is so inconceivably low that the chance of it finding fuel is almost zero. It is a perfect dark object, its presence betrayed only by the rare, perfect alignment for gravitational lensing. This environment offers the cleanest, most unambiguous test of our theories, but also the most challenging detection scenario. The second environment is the interior of a massive galaxy cluster. This changes everything. A cluster is a metropolis of hundreds or even thousands of galaxies bound together by gravity, but the space between those galaxies is not empty. It is filled with a searingly hot, thin soup of gas known as the intracluster medium. This gas, heated to millions of degrees, glows faintly in X-rays, and it is everywhere within the cluster's vast gravitational domain. For a black hole wandering here, the rules of engagement shift. It is no longer in a perfect void. It is moving through a diffuse, hot atmosphere. As it plows through this tenuous gas at high speed, it can act like a boat moving through water, creating a bow shock. More importantly, some of that hot gas can be captured by the black hole's gravity, funneled into a faint, slow accretion flow. This process would not create the brilliant quasar beacon of a well-fed black hole, but it could generate a faint, persistent glow of X-rays. This is a crucial distinction. A wanderer in the true intergalactic void is a pure gravitational lensing target, completely dark. A wanderer within a galaxy cluster could be a multi-messenger object. We might detect it first through its faint X-ray signature, a soft, high-energy whisper against the diffuse glow of the cluster's own hot gas. Finding such an X-ray source positioned away from any galaxy's core would be a major clue. It would point to a massive, compact object doing just enough feeding to betray its location. This creates a second parallel hunt. While telescopes like Vera see Rubin scan for gravitational lensing distortions, X-ray observatories like Chandra are meticulously mapping the hot gas in galaxy clusters, searching for anomalous, point-like sources that do not correspond to a galaxy. A combination of signals, a faint X-ray point with a coincident gravitational lensing distortion, would be the holy grail, confirming not just the presence of a dark giant, but also giving us insights into its immediate environment and behavior. The type of darkness a wanderer inhabits directly shapes how we must search for it, turning a single mystery into a multifaceted chase across the spectrum of light itself. The absence of a central anchor does not leave a galaxy unchanged. When a supermassive black hole is violently ejected from its core, it creates a profound vacancy, a missing heart in the galactic body. This event can fundamentally alter the galaxy's future. In its active phase, a central black hole does more than just consume, it also regulates. The immense energy released from its feeding process floods the galaxy with radiation and powerful jets of particles. This energetic feedback acts like a cosmic thermostat, heating up surrounding gas and preventing it from cooling and collapsing too quickly to form new stars. It is a balancing act, a way of pacing a galaxy's growth. Remove that regulator and the delicate equilibrium is shattered. Vast reservoirs of cold gas, no longer held in check by that central energy, could collapse in a sudden, frantic burst of star formation, a brief, brilliant starburst that consumes the galaxy's fuel in a relative instant. Alternatively, without the black hole's gravitational influence, the orderly rotation of stars at the very center could become chaotic, potentially leading to a puffed-up, diffuse core. The galaxy, in essence, loses its primary engine of self-regulation. Its evolutionary path is stunted or sent spiraling in a new direction, forever marked by the ancient trauma of losing its most massive resident. This means the galaxies we see today, with their quiet, well-behaved centers, might be the lucky ones whose anchors held firm, while others, with unusual cores or strange histories, could be the survivors of a violent expulsion we are only now learning to read. But the story of these wanderers is not solely one of loss and absence. A rogue black hole on its endless journey is not an inert stone, it is a gravitational scythe moving through the cosmic field. As it passes through the sparse, cold clouds of gas that drift in the intergalactic void, its immense gravity can act as a sudden, violent trigger. Picture a vast, quiet cloud of hydrogen drifting for eons in the dark. The black hole's approach creates powerful shock waves and compressions within the cloud. These forces can crush pockets of gas, jump-starting the process of gravitational collapse that leads to the birth of new stars. In this way, a dark wanderer could leave a trail of stellar formation in its wake, a faint, linear constellation marking its passage through the nothingness. It becomes a paradoxical creator, an object of ultimate darkness seeding points of light. This seeding effect could be even more dramatic if the wanderer encounters a small, fragile dwarf galaxy. A close flyby from a billion solar mass phantom would wreak gravitational havoc. Its tidal forces could strip away gas, distort the dwarf's shape, and ignite bursts of star formation or, conversely, tear existing stars from their orbits, leaving behind a disrupted, misshapen remnant. These subtle distortions, these archaeological scars in the structure of small galaxies, could be another way we detect the ghosts. By surveying populations of dwarf galaxies and looking for those with unusual shapes, unexpected star formation histories, or signs of internal chaos that cannot be explained by interactions with their normal neighbors, astronomers might find the faint fingerprints of a dark giant's passage, a billion years after the event. The universe keeps a slow and patient record, and the evidence of these phantoms may be written not in their own light, but in the altered fates of everything they passed by. The physics of this cosmic ejection is both elegant and brutal, governed by a sequence of celestial hurdles. For two supermassive black holes to merge and create a wanderer, they must first overcome what astronomers call the final parsec problem. After a galactic collision, the two black holes sink to the new center, orbiting each other at a distance of about 1 parsec, which is roughly 3.26 light-years. At this separation, their gravitational pull is strong enough to fling nearby stars away, but not strong enough to efficiently rob each other of orbital energy. They enter a kind of gravitational stalemate, a slow dance that could, in theory, last longer than the current age of the universe without some external help. They need a third party to break the deadlock. This often comes in the form of a third black hole, perhaps from another merger, or a dense cluster of stars that can interact with the binary, stealing energy and allowing the pair to spiral ever closer. Once they push past this final parsec barrier and enter the last few thousand kilometers, their fate is sealed by the pure geometry of spacetime itself. As they whip around each other at a significant fraction of the speed of light, they churn the fabric of the universe, emitting those powerful gravitational waves. Crucially, if the merger is asymmetric, perhaps because the two black holes have different masses or their spins are misaligned, the gravitational waves are shot out more powerfully in one direction. The conservation of momentum demands a reaction. The newborn black hole recoils in the opposite direction, like a rifle kicking back after firing a bullet. The speeds imparted by this gravitational wave recoil can be astonishing. Simulations show they can reach several thousand kilometers per second. To escape the gravitational pull of even a massive galaxy, a speed of around 2,000 kilometers per second is often enough. The most powerful kicks can therefore launch the merged black hole clear out of its galactic home, sending it on a one-way trip into the intergalactic void, a silent projectile forged in the final instant of a union that destroyed its own anchor. This violent birth certificate is written in the mathematics of relativity, a signature of how the most massive objects in creation can be turned into the fastest exiles. Our hunt for these dark giants is not without clues already hidden in plain sight. Across the cosmos, astronomers have catalogued a series of strange, persistent anomalies that defy easy explanation within our old models. These cosmic puzzles may be the first indirect evidence of the Wanderer's passage. One of the most compelling is the case of offset active galactic nuclei. We find galaxies that shine with the brilliant, energetic signature of a feeding supermassive black hole, but that beacon is not at the galaxy's geometric center. It is displaced, sometimes significantly, as if the engine of the entire system has been knocked askew. One leading explanation is that we are witnessing a black hole that received a powerful gravitational kick, but not quite enough to escape entirely. It is now oscillating around the galactic core like a bell that was struck and is still ringing, dragging its brilliant accretion disk with it on a slow, lopsided orbit. This could be a snapshot of a near miss, a wanderer in the making, still clinging to the edges of its home. Then there are the orphaned jets. We see immense, powerful streams of plasma shooting out from what appears to be empty space, with no visible galaxy or quasar at their source. These jets are the hallmark of a supermassive black hole's intense activity, but the central engine itself is missing from our images. Could the source be a rogue black hole, actively feeding on a rare cloud of intergalactic gas as it travels, its brilliant jets visible from across the universe while its dark body remains hidden in the void? The jet points back to a location of profound darkness, a signature with no signer. Closer to home, within our own Milky Way, we observe hypervelocity stars. These are stars rocketing through the galaxy at speeds so great they are unbound, on a trajectory that will eventually fling them out into intergalactic space. Their origins are a mystery. Some could be flung from the chaotic center of the galaxy, but others have paths that trace back to seemingly empty regions of the galactic disk. One provocative theory suggests an invisible driver, a close gravitational encounter with a massive, compact object. A wandering intermediate mass or even a small supermassive black hole passing silently through the galactic plane could have acted as a gravitational slingshot, launching a star to incredible speeds and then disappearing back into the dark, leaving only the speeding star as evidence of its unseen passage. Each of these anomalies, from off-center engines to phantom jets to runaway stars, is a question mark in our data. Individually, they have other possible explanations. But collectively, they form a pattern of cosmic irregularities that point toward massive, unseen objects influencing their surroundings from the shadows. They are the circumstantial evidence in an ongoing investigation, hints that the universe is more dynamic and more densely populated with dark giants than our traditional maps have ever shown. Finding a direct, unambiguous rogue would be the key that turns these puzzling clues into a coherent new chapter of cosmic history. The anomalies we see today are merely the prelude to a coming revolution in observation. The next decade will see the launch and operation of two monumental observatories designed to stare into the dark with unprecedented patience and scope. First, the Nancy Grace Roman Space Telescope, set to launch around 2027. Unlike the Hubble, which focuses on deep, narrow fields, Roman is built for the grand survey. Its primary instrument will have a field of view over 100 times larger than Hubble's infrared camera. This is not a telescope for studying a single galaxy in detail. It is a machine for taking a cosmic census. A key part of its mission is a dedicated microlensing survey toward the center of our galaxy, where stars are densest and alignments are more probable. But Roman's power lies in its combination of scale and infrared vision. It will peer through the dusty veil of the galactic plane, monitoring hundreds of millions of stars for the telltale brightening caused by foreground objects. Its infrared eyes are perfectly suited to spot the faint, cool objects that could be imposters, like brown dwarfs, allowing it to efficiently filter them out from the true, perfectly black candidates. Roman will not just find more events, it will characterize them with a statistical power we have never had, building a robust population model of dark objects in our own galactic backyard. On the ground, a complementary giant is awakening. The Vera Rubin Observatory in Chile will begin its legacy survey of space and time, LSST, in the next few years. Its task is to create the greatest astronomical movie ever made. Every few nights, its enormous 3.2 billion pixel camera will capture the entire visible southern sky, repeating this cycle for an entire decade. This relentless, all-seeing gaze is designed to catch change, to document anything that moves, flickers, or appears. For microlensing, this is transformative. While Roman will conduct deep, targeted surveys, Rubin will cast the widest possible net, scanning the whole sky. It will detect microlensing events not just in our galaxy, but potentially caused by objects in the vast spaces between galaxies. Its strength is in volume and time, finding those long-duration events that last years, the kind that could signal a slow-moving, supermassive object. Together, Roman and Rubin represent a paradigm shift. They move us from the era of hunting for rare, individual events through luck and persistence into the era of big data astronomy. They will not merely look for needles in a haystack. They will map every strand of hay in immense detail so that the subtle disturbance caused by a single, heavy needle becomes unmistakable. They will generate millions of microlensing alerts, a flood of potential clues. The real discovery will then happen in the quiet rooms of data centers, where advanced algorithms will sift through this ocean of information, searching for the statistical outliers, the events that are too long, too massive, or in the wrong place to be anything ordinary. The odds of finding our phantom will no longer be a cosmic lottery, but a calculated probability based on scanning nearly the entire sky, nearly all the time. The dark is about to be illuminated by the relentless gaze of two new sentinels, and what they reveal will redefine our place in the cosmic story. The ultimate ambition, however, lies far beyond statistical inference or fleeting distortions. It is the dream of turning our phantom into a portrait, of seeing the unseeable directly. Today, our best image of a black hole is the now iconic orange ring of Messier 87's core, a monumental achievement by the Global Event Horizon Telescope Network. But that image is of a black hole drowning in light, surrounded by a furious, brilliant accretion disk. Our wanderer has no such luminous finery. To image its stark reality would require a telescope of almost unimaginable scale and precision. The path forward stretches into the speculative future, toward an instrument not confined to our planet. Imagine the Event Horizon Telescope concept expanded into a fleet of radio dishes orbiting the Sun, forming an interferometer with a baseline as wide as the inner solar system. This virtual telescope would have a resolution so sharp it could, in theory, resolve the immediate environment of a nearby isolated supermassive black hole, perhaps one drifting quietly within our own galactic neighborhood. Instead of a fiery ring, what might we see? The prediction is a perfect dark silhouette, a black sphere set against the background glow of the universe, its edge defined by the ghostly lensing of stars and galaxies directly behind it. This shadow would be the event horizon itself, or more precisely, its photon ring, the very outline of no return. Such an image would transform the object from a gravitational abstraction into a tangible, visible entity. It would allow us to measure its shape with exquisite detail, testing if it is perfectly spherical as general relativity predicts for a non-rotating black hole, or oblate if it carries a spin. Every subtle deviation in that dark circle's profile would be a data point speaking to the fundamental nature of gravity under the most extreme conditions. Another futuristic concept, X-ray interferometry, could probe even closer. By precisely combining X-ray signals from multiple spacecraft, we might one day resolve the innermost stable orbit, the last place matter can circle before plunging inward. For our perfectly isolated wanderer, this region would be hauntingly empty and dark, a clear demonstration of a black hole in its purest, most quiescent state. The engineering challenges for such endeavors are staggering, spanning decades or even centuries of advancement, yet the goal crystallizes the entire purpose of the hunt. We are not just searching for missing pieces in a cosmic puzzle. We are striving toward a future where the darkest objects in creation are brought into the light of our understanding, not by the glow they create, but by the exquisite shadow they cast upon the fabric of reality itself. Finding a single phantom would be a triumph, but confirming a vast population of them would rewrite our cosmic ledger. For generations, our fundamental perspective has been geocentric in a galactic sense, assuming that mass and meaning are concentrated at the heart of things. We built our understanding of cosmic structure on the idea of central anchors, of supermassive black holes as the fixed points around which galaxies coalesce and evolve. This search for wanderers challenges that comforting hierarchy at its core. It proposes a universe where the heaviest objects are not necessarily the stable centers of order, but can be the ultimate free agents, the nomads born from chaos. This is more than just adding a new category to an astronomical catalogue. It is a philosophical shift from a cosmos of settled kingdoms to one of drifting empires, from a map of fixed capitals to a chart of dark continents in motion. The center, we must learn, does not always hold. Sometimes the center is ejected, leaving behind a silent question and a trail of disrupted gravity. This realization forces us to revise our most basic inventory of what the universe contains. Our census of matter, of mass, of gravitational influence has been conducted by looking at the light. We counted the brilliant beacons in galactic cores and extrapolated from there. But if a significant fraction of supermassive black holes are dark and drifting, then our accounting is fundamentally incomplete. We have been tallying the mass in the bank vaults while missing the fortunes carried in unmarked cases across the border. These nomadic relics are not failed or insignificant. They are the direct products of the universe's most violent formative events, the mergers that built the galaxies we see. Each wanderer is a fossil, a preserved record of a cataclysm that occurred billions of years ago. Its mass, its velocity, its trajectory all encode the details of that ancient collision. Finding them transforms the intergalactic void from an empty stage into an archive, a silent museum housing the artifacts of cosmic violence. The darkness between the stars is not simply empty, it is curated, holding the exiled results of creation's most decisive moments. This shifts our entire narrative. The story of the cosmos is no longer just about the grand structures that survived and shine, but equally about the dark remnants that were cast out in the process. It asks us to consider that the true history of the universe might be written as much in the things that were lost to the darkness as in the brilliant cities of light that remain. This grand synthesis of the hunt leads us to a startling possibility. For decades, the quest to identify dark matter has been a search for the exotic, for a new, undiscovered particle that exists outside the standard model of physics. We have built immense detectors deep underground, hoping to catch a fleeting whisper of these hypothetical entities. Yet all the while, a classical, well-understood candidate has been drifting in the darkness, hiding in the most profound way possible. Rogue supermassive black holes represent a form of dark matter so perfect it borders on irony. They are not a mysterious subatomic particle, but a colossal, astronomical object whose nature we comprehend completely. Their darkness is not a quantum property, but a simple consequence of their environment and their own physics. They do not weakly interact with light, they utterly consume it, leaving no trace. This makes them the ultimate gravitational entities, massive anchors of pure gravity that influence the cosmos on the largest scales while remaining virtually invisible on any other. They are dark matter in its most literal, classical, and elegant form. They have been hiding in plain, dark sight all along, not because they are made of something strange, but because they are so perfectly, completely black. This reframes the entire mystery. Perhaps we have been looking for the missing mass in the wrong place, with the wrong tools, and at the wrong scale. Our particle detectors listen for faint pings in the quiet of a lab, while the true answer may be drifting in the silent vastness between galaxies, detectable only by the patient, collective observation of its gravitational sway over the light of the entire universe. The discovery of a population of these wanderers would not merely add a new object to our charts, it would offer a profound and elegant solution, bridging the gap between the known physics of black holes and the unknown nature of the cosmos's hidden mass. It suggests that the universe's greatest secret may not be a new form of matter, but an old one we simply could not see. The journey from a theoretical prediction to a tangible hunt is a story of scientific imagination meeting relentless patience. We began with equations and simulations which whispered of violent births and gravitational exiles. These ideas painted a universe far more dynamic than our static maps, one where the heaviest anchors could be cast adrift. That theoretical possibility demanded evidence, launching a decades-long search for phantoms in the deepest dark. We refined our methods, moving from hoping for chance alignments to building machines designed to watch the entire sky, to measure the slightest tremble in a star's position. We found our first isolated black hole not by its light, but by its gravity, a proof of concept that validated the entire, painstaking approach. Now, with observatories like Vera, Rubin, and the Roman Space Telescope coming online, we are transitioning from a hopeful search to a systematic census. The mystery persists, a quiet question hanging in the intergalactic void. Yet for the first time, we are not just asking the question, we are building the instruments that are almost certain to provide an answer. This pursuit embodies a profound humility at the heart of cosmology. We must accept that the universe's most massive, most consequential secrets may not be blaring in brilliant quasars at the centers of galaxies. They might instead be the silent ones, the dark wanderers, drifting unnoticed through the endless night, waiting only for a single, fleeting flash of bent starlight to finally step into our understanding.